First of all, we had a change to some of the coverage. So you have my apologies that this changed from Monday afternoon basically to Tuesday morning. That's because the instructor team meets on Monday nights, so this does occasionally happen. Essentially, we got rid of section 15.4 and moved it to exam 4. So that announcement did go out. It's also hanging out in the announcement section of the 701 section. So what I'm going to do is I'm going to be addressing questions that are both from my class as well as the last question from the exam review. So I'm going to hit a couple of the ones that I can do quickly that are from my class. So this says, chapter 17, from one of the questions we plugged each X we found back in and took the answer 3 times. This thing was called successive approximation. That's what they're talking about. In what scenarios would we do that? So essentially, the only time we would actually need you to do that is this would just be an option. We don't actually force you guys to do that this semester, at least. So this is basically just an option that you could use instead of the quadratic. But I will tell you that we still have a really big emphasis on using that X is small approximation. Basically all of the time. So you guys have been using the X is small approximation. Just keep at it. Keep using the X is small approximation because that really is, this exam has enough calculations on it that we basically designed them so that you just need the X is small approximation. But I covered successive approximation in the case that it got included. Then I'm going to flip over to this side on the right. Why is this the hardest test? I frankly blame spring break. This is my big spiel about this. And then the other thing is that you still need most of the exam 2 material. So the hard thing is that for some folks, exam 3 is nice because it still is a lot of acids and bases in equilibrium, and that still is what the material is over. For other people, there was stuff about acids and bases in equilibrium on exam 2 that they didn't like, that they still had some questions on, and those questions remain, and those problems are now a bit more difficult because they're still trying to deal with how to identify an acid and a base. So there are some folks still out there still working on identifying conjugate acids and bases. And for those folks, this material is harder because that is a skill that we basically assumed that you learned and are still using. And for some folks, they forgot it over spring break and they had to get it back. So that's usually why this exam is harder, is because if the exam 2 material is still a problem, then this exam is not going to help that. Are we going to be given a lot of time taking problems? I forgot how many questions there were. I think we have 26 multiple choice plus 2 short answer. And I will tell you right now, I would actually recommend you do those short answer first and knock them out. Because yeah, I would actually recommend you guys do the short answer first on this exam to get those done and out of the way. Because you're not wrong. Those BCA tables do take longer because it's a 2-part, those titrations are 2-part calculations, and so they just take more time. But what we have right now is the short answer being worth 12 points total. So there's still 2 questions, but right now, and it might change because this is only Wednesday morning. But right now, those 2 short answer questions combined are worth 12 points. So yeah, I would recommend you guys do the short answer first. Is there a good way to organize the different ways to use titration equations, like when we have strong bases versus weak bases? So I went ahead and left this one in here. I actually tried to address this one during the exam review, but there are times when questions are asked in different ways and it feels like a different question. So I'm going to come back up to here where I've got titrations and I've got 3 kinds: strong acid, strong base, weak acid, strong acid, weak base. And that the very first step is to react in moles. So as far as what kind of equations do we use for titrations, if you have a strong species, you are headed for that BCA table and you are going to react in moles. So that's the first step for any titration, no matter what. So first thing, react in moles. Then this is the part where I didn't talk about equations, but we can go ahead and go back in and add this. So when you're talking about strong acid, strong base, there's essentially three options: strong acid left over, strong base left over, or neither, and the pH is 7. So that last one where it's at the equivalence point, because that's the other thing. So I'm going to go through, oh, apparently I'm highlighting the equivalence point in yellow. So that's the equivalence point. So when I am at the equivalence point for a strong titration, there is no equation for that. Because essentially the argument is everything you have is neutral. You have water, you have a neutral salt, nothing happens. If you have strong acid left over or a strong base left over, you're headed for similar paths, but slightly different. So if it's number 1 and we're talking about the strong acid leftover, you are headed for just the pH equation. Now that does mean that you need molarity. So that lovely reminder that these brackets here mean molarity. So you are going to have to take at the end of the BCA table, the end of the BCA table is in moles. So you are going to need to find moles divided by final volume, or total, maybe total is a better word, total volume. And then just plug in to the pH equation. So if that's where you're at for a strong acid left over, then that's all you need. If it's a strong base, on the other hand, that's the one where what you're going to have left over is you're going to have leftover hydroxide. So that's the only tricky part there. You still have to deal with moles over total volume, but then if you just plug that and take the negative log of whatever that number is with strong base, you'd have POH. So since you'd have POH with strong base, you got to do the 14 minus the POH to get the pH. So again, the equations to me are similar to each other because you're still going moles over total volume and then plugging them into that negative log equation, but that's all that we're doing. So in that case, things are a bit similar. Taking a look at the strong base, weak acid, and the strong acid, weak base, because I've got the first thing is the same on both of those, which is a buffer. So those two, at least, if you are before the equivalence point, if your react in moles tells you that you have both, hold on, Riker, enough. I know you want my attention. Sorry, my dog would appreciate more attention from me. So if what you get out of the BCA table is both the weak acid and its conjugate base, or both the weak base and its conjugate acid, you're headed for a buffer. So here, if we are dealing with number 1, then we are dealing with the Henderson-Hasselbalch equation. Personally, so again, to me, it's up to you whether you like both versions of the Henderson-Hasselbalch equation, or if you just like one of them. But again, you guys should be able to use the Henderson-Hasselbalch equation to find pH, or you could use the Henderson-Hasselbalch equation to find POH, and then use the 14 minus again. But both of those are buffers, so both of those should use the Henderson-Hasselbalch equation. I'm going to skip the equivalence point on these two real quick and look at the fact that number 3 is strong base. So if I have strong base, weak acid, if I go past the equivalence point, I should have strong base left over, in which case I am actually doing things the same way that we did things for just having strong base left over from the previous strong titration. So if all I have is strong base left over, then I just have to deal with the strong base. I still need moles over total volume, but then I'm plugging into the POH equation. So I'm using the same equation from before. Same game. If I'm on strong acid, weak base, and I go past the equivalence point, I'm on strong acid leftover. I am also using the number 1 now over here, same as strong acid leftover. where all I need is pH is equal to the negative log. So we've now talked about, out of the 9 options that I have on my on this, right? Because I've got 3 options for each of the 3 titrations. We have talked about pH equals this the negative log of the proton concentration, and that applies to 2 different situations, both my strong titration, and it also applies to the strong acid titration. So basically, whenever you have strong acid, that pH equals negative log of the proton concentration is a way to solve the problem if strong acid is what's left over. And if I have strong base in my titration, here's strong base on the strong acid, strong base, here's strong base in strong base, weak acid. If that's the case, and I have strong base left over, which can happen, then what I have is I deal with the POH version. So again, there's 2 different scenarios where that equation comes into play. If I have a weak thing, weak acid or a weak base, then there's a possibility that I'm going to have a buffer. So we've actually only looked at 3 different equations, but we've covered 6 different scenarios, right? 1, 2, 3, 4, 5. Yeah, 6. So 3 equations, but each of those equations covers 2 different sets of scenarios in titrations. The other thing we covered, so that was 3. 4 was there is no equation, you're just at the equivalence point. So the last thing to cover all of my equations for all of the things is dealing with the equivalence point of either my strong base, weak acid, or my strong acid, weak base. These do take the longest because at those equivalence points, you have only one thing left in the titration, and you have to do an ice table. So then therefore the ice table then does take more time. So taking a look at this, if we did strong base, weak acid, then you're dealing with something like OH plus HA, and that just gets you that A minus. So if I'm at the equivalence point for this in my BCA table, then I only have whatever the amount of my weak base is. So then my weak base is what mixes with water, and I get hydroxide. So for a strong base, weak acid at the equivalence point, not only am I going to need to deal with an ice table, but I'm also going to have to deal with the fact that that ice table produces hydroxide. So I would still need that POH equation by the end. If I'm doing the other one, strong acid, weak. So here's the thing that I don't know. Whenever people ask me questions about organizing titrations, at this point, I've talked about how to organize this for so long, I frankly lose my confidence that this becomes helpful because this is a lot of different scenarios, but I'm almost done, so I'm going to finish this out. Strong base, weak acid at the equivalence point. It's the only one I haven't talked about yet. So if we're doing strong acid plus a weak base, that would make the conjugate species. For an equivalence point, we're talking about these being 0. So this is the only thing we have, the conjugate acid in solution. A conjugate acid in solution is going to produce protons. So when you do your ice table, you do get to just plug your X value into the negative log or pH. So those are all your scenarios. So those are all the scenarios. So there's 9 essentially options for all of the titrations because it's always before, at, or after the equivalence point for each of 3 titrations. And so by the time you do all of those, you only have certain options based on what you have left in solution. So I hope that helps. I'm back. Okay, so I tried. For the exam, we'll need to memorize solubility rules. I'm going to just go say no. No, you have KSP. In my class, I did talk about what I think is potentially helpful, which is sometimes knowing that your alkali metals are always soluble. Frankly, I think is helpful, but at this point, if you don't think that's helpful or you don't have time, then don't worry about it. You can just look for KSP. I'm sorry, I'm going to chew with my mouth open a little bit. Or how to draw Lewis structures. No. Anyone wondering why they're asking that? That is from Lewis acids and bases. But either we will draw it for you, or we'll provide the reaction in such a way you don't need that. What's the purpose of buffers? The purpose of a buffer is to maintain a pH. So this is why when we talk about buffers, usually we start by talking about blood, because your body needs to maintain a particular pH, and buffers are how that happens. So when you do different activities, your body does produce more acid or more base. Your body can also take in things that will make that happen. So for example, carbon dioxide is one of the ways that this is all controlled and regulated. So if you are breathing in different ways, sometimes you can change the amount of carbon dioxide that you have in your lungs, and that will change that pH. But you don't want that to change your pH a lot. So we have buffers to maintain pH. That is important also when you think about like little fishes living in streams and lakes and oceans. They also need to maintain pH. I'm going to do a math problem now. No. So I'm hoping this helps answer some of the other questions I've seen. Because there are questions especially about how to set up reactions. So here we go. A beaker contains a volume. That's what that is. And then there's a molarity of a particular acid. It says K in the table above. Whoopsies. 3.0 times 10 to the negative 8. I wrote it over here. And here's another molarity of this other thing. To this is added 15 milliliters of 0.25 molar sodium hydroxide. What's the final pH? So one of the things to note in this problem, first of all, is I have a strong species. Because I have a strong thing, no matter what that is, that thing has to react. So I need a BCA table. So therefore, I have to have moles. Period. End of story. We haven't even really addressed the other things in the table, but I am asked about pH. But I have a strong species. I have to react away the strong species because I can't keep it. It won't work. So I take 0.015 from my volume and 0.25 for my molarity to get moles. That's 0.00375 moles. BCA table is always in moles. So I have a strong thing, so that's in moles. Cool. Now, I have two things. I have HClO and I have NaClO. I need to think about this thing for a minute because HClO says Ka in the table above, which means that's a weak acid. And frankly, I have a strong base. Those things are going to react together. And so when I think about those reacting together, I can absolutely just go ahead and write my reaction. And when I do that, I can actually see that this thing here is the same as this thing here. But if I didn't do it that way, also acids react with bases. So acids either are going to react with other acids, but we know that that's not true. We've studied titrations. Acids and bases react together. So that's the way I made that decision. So let's talk about this thing for a minute, because one of the other questions I also got was about salts. This is a salt. So first of all, a periodic table is really helpful, because in your periodic table, if I want to think about that first thing is sodium, that sodium should have a +1 charge. So I am relying on being able to recognize an alkali metal. You have periodic tables on the exam, so you don't have to have those memorized. You have a periodic table. So that means that this thing breaks into this thing and that thing. Then the game is I need to recognize that this won't affect pH. There are different ways you could know that, but there is in fact a slide in the notes from chapter 17 that basically just says alkali metals and alkaline earth, except for beryllium, because beryllium will affect the pH, don't affect pH. So there are a lot of different ways to talk about why that's true. If you would like a more in-depth explanation, then I'm going to tell you that that's an office hours question, because there's different ways to explain it. But as we get closer to the exam, I'm just going to tell you there's a slide in the notes that this is true. So, this thing, it's negative. And in the problem, it's negative, so it's likely a base. So we're going to say, what if we added H plus? So if we added H plus to this thing, it'd look like this. This then should look like a weak acid. So the thing that we actually have, which is the thing in blue, we have this. So that is a base. It's a weak base. The thing I wrote in red down here would be its conjugate acid. So we are relying on y'all to be able to essentially recognize that if you have a negative thing in a salt, you need to consider, is this thing a base? Is this thing a base? We're looking for, is it a conjugate of a weak acid? Or is it a weak base and you could draw a weak acid as its conjugate? But we're looking for these to be weak species is what we're looking for. Oh. So in the problem, I have HClO and I have NaClO. I therefore have a weak acid and its conjugate base. I have molarities for both of those, which means, even though the problem never said this, that means I have a buffer. So this is actually a buffer problem. Now, here's the other question I get asked a lot, which is, but I have all these things, but yet I put one of them on the product side. I did. Here's the deal. The whole point. So first of all, conjugates need to be on opposite sides of the reaction arrow. If they are conjugates of one another in acid-base reactions, because we are likely to be going back and forth between them, The conjugates have to be on opposite sides of the reaction arrow. Like it or not, they need to be. The other thing is that because this is a buffer, because I've got one thing, because I've got a weak acid and its conjugate, that's a buffer, they go on opposite sides of the reaction arrow. The whole point of a buffer is that it can react with either acid or base. The way that it does that is by being in equilibrium with itself. So even though I have a straight arrow drawn here, I have a straight arrow drawn because of the strong thing, because that's going to react. But the idea is that my buffer goes on opposite sides because I could think about either part of my buffer reacting to make more of the other part of the buffer. So my buffer needs to be able to respond to either strong acid or strong base. And the way that it does that is by being on both sides of the reaction arrow. Sorry, that big sigh for me is because I get to the point where I don't know better ways to describe things, and I feel like there should be. There are also some like ways to physically do these, like manipulative style, like having like physical pieces to move around, and that might be helpful, but I also can't do that in this particular setting. So what I'm writing in here are the moles, by the way. So again, this is a BCA table. Everything needs to be in moles. So since I'm in a BCA table, everything is in moles. Also, since I'm in a BCA table, that means in my after set, something goes to 0. That's going to be the smallest. So the smallest number gets subtracted. So that is going to be this guy. Now, on the other side of my reaction arrow, it's not subtracted, it's added. So just like when we used x in other places, that idea of minus x plus x, because I'm on the other side of my reaction arrow. My strong base reacts with my weak acid. It produces my weak base. I need to reflect that in my mathematics. So I get no more. I use up all of my strong base for the weak acid. I do the subtraction. I get 0.0125 for my weak base. 7.5. So now I have pieces. I don't care about the water. I make water, but I don't care. It's not going to be part of the pH. So now what I have is I have weak acid and I have weak base still. My amounts changed, but I still have weak acid and I still have weak base. So because I still have both of those, I get to use my Henderson-Hasselbalch equation. We can, by the way, go over to that potentially useful information page because it is on there. I know I just wrote it from memory, but Henderson-Hasselbalch, there it is over here. So Henderson-Hasselbalch is on that potentially useful information page. You don't have to have that memorized. It's right there. So pH is the thing I'm looking for. pKa, I'm going to come up here. I have a Ka value of 3 times 10 to the negative 8. So I'm going to take the negative log of 3 times 10 to the negative 8 for my pKa. And then my log, I need the A minus on top. So I need the base on top, 0.03. And then I need the weak acid, 0.0125. There's one other question I'm going to try to go back and answer to try to anticipate other questions y'all might have. That's not what I want to do. So I get the pKa to be 7.52, and then this is 0.03 divided by 0.025, and I take the log of that number, and that is a positive number. I have more base than acid, so my pH should go up. And it does. 7.9. Ta-da! So there we solved this problem. One of the other questions I anticipate, so in my reaction, because I've gotten a variety of questions about the reaction. So what I am going to do is we're just going to have a little follow-up conversation about the reaction. So here's the deal. I wrote this reaction. This would be kind of like your total reaction. It's got everything in it. But there was a time where we wrote ionic reactions. And ionic reactions would look something like this, where we had all of the pieces written out as long as they were completely soluble or strong electrolytes. Then we'd have a time where we'd be like, but that sodium happens on both sides and it's not going to affect the pH. So therefore, we're really going to deal with this. This last thing is what we refer to as the net ionic reaction. The nice thing about the net ionic reaction is it gets rid of some of those other things that don't affect the pH. Some of those things that we're ignoring anyway can be helpful. But that way I am just dealing with my strong base. And that way I can kind of more easily see how my conjugates come into play because they look a little bit more similar to each other in that net ionic reaction. So that is your net ionic reaction. You guys should know and recognize that term of net ionic reaction. Okay. What else is in my list? Identifying salts as basic, acidic, and neutral. So I'm going to try to do this in a way that I hope makes sense. Salts. Here's the deal. Salts always have a positive thing. We call that a cation. It goes first. And they always have a negative thing. That's an anion. It goes second. Basically, you're going to ask yourself two questions. You're going to ask, is the cation acidic or neutral? For the purposes of this course, you are going to assume that those are the only two options. I don't care what other interesting options the internet showed you. I don't care what ChatGPT said. And I don't care what other interesting way you think that we can mess with you. I am telling you that I've already taken your exam, and I'm telling you that your question on salts is the cation acidic or neutral? Whew, I think I need more sleep, y'all. I'm real sorry. I sounded real mean all of a sudden. Oh, and then you're going to ask yourself, is the anion basic or neutral? Is the anion basic or neutral? These are the questions we're trying to ask. So when you have a salt, like so we'll do a different one. This guy. This has a positive and a negative charge. You have to find them. A periodic table can help. So I've got chlorine in there. Chlorine's way over here. That's got a -1 charge. So being familiar with your periodic table and what it can tell you is part of the skill here. So that means when I'm trying to assess this, I'm trying to assess my cation as being NH4+. I'm trying to assess my anion as being Cl-. In both cases, I'm basically going to consider what I have and what the conjugate looks like. That's how I'm going to do this one today. I'm going to look at I'm going to look at the ion, and I'm going to look at the conjugate. This is a thing. If I was to have a conjugate of this already has a positive charge, which means if it was going to have a conjugate, it would look like this. That's a base. This is an acid. More specifically, this is a weak base. So this thing is a weak acid. So I have evidence that this is an acidic salt. Then I have this chlorine. Let's take a look at what happens when I do this. We need to then add if anything was going to happen to something with a negative charge, it would have to react with water. This is the part that you guys are not going to like, but you have, so one, I don't actually have a simpler way to do this because of the halides don't tell the same story all the way through. So this now looks like I've written a reaction where I have a base, have drawn an acid and a base. So this looks now a lot like what I just did, but there's something that's a little bit different. This is a strong acid. Strong acids ionize 100%. So this thing immediately goes to make H plus and Cl minus. So this immediately makes H plus and Cl minus, which means that this doesn't really stick around. I don't really actually have this because if that HCl was created, it would immediately fall apart. And then when you look at it, then I wind up with water and the chloride ion. And that's what I started with. Here's the water, there's the water, here's the chloride anion, there's the chloride anion. So the thing is that we can consider that anion to see if it's a base, but what happens is since it's a base of a strong acid, it can't really act like a base. It doesn't actually get to do it. We can imagine what would happen if it did, so we can kind of play that what if game. But when you play that what if game, you see it having a conjugate that's a strong acid, and therefore that conjugate doesn't have any power to actually act like a base. So this is not really a base. So this is neutral because of the fact of the other part was strong. So that's actually neutral because if it was to do anything, it would make something that was strong. The strong thing changes immediately, so you don't actually get that reaction. So is the cation acidic or neutral? The cation was acidic. Is the anion basic or neutral? The cation is neutral. So therefore, when you're looking at it, that means that the salts that we're trying to investigate overall is an acidic salt, because you do in fact have part of it that acts like an acid. So that's the methodology for identifying if salts are acidic, basic, or neutral, is you're gonna have to analyze both the cation and the anion for each one. I will also say that I personally think this gets faster the more you practice this, which is to say that if you notice that the thing reminds you of a strong species, that strong thing means that the thing you actually have is neutral. And I know that that bothers some of you. If that bothers you, go back to the video, rewind it, and replay this, because that notion that something is neutral because it can't do anything, it doesn't actually get to act. That's what we're talking about when we say something is neutral. We can imagine that it happens, but in reality, it doesn't actually go anywhere. This just says when all the reactants are gone, it's been neutralized. That is for your BCA table. And titrations. That's a yes. When we write an equation for the BCA table or ice table, how do we know if the acid or base will be the products or reactants? So here's the thing. I'm going to say that I answered this question when we looked at, okay, no. How do we know if the acid or base will be the products or the reactants? So this is the part of this question I'm going to nap. How do we know if the acid or the base will be in the products or the reactants? So here's the thing. One, what is given in the problem? because one of these problems is potentially like the buffer question that we did, where you had a weak acid, a weak base, and a strong thing. At that point, then figuring out what goes in the products and what goes in the reactants is tricky because there's all kinds of stuff happening. But in general, if you have a strong thing, the strong species, I don't care if it's an acid or a base, is a reactant. It has to be. You have to get rid of it. You're also therefore using a BCA table to react in moles. If you have a strong species, you are putting that into a table where you can react in moles. So the strong species, automatically, this is what's happening. From there, your weak species has to react with the strong one. So therefore, if you have a strong acid, you pair that with the weak base. If you have a strong base, you pair that with a weak acid. So if you have a weak species and you're trying to decide, you're looking for pairs. So that would all be about the reactants, which means your product has to have the conjugate. So hopefully that helps. The conjugate of the weak. Hopefully that helps. Take a look back at some of the examples we've done before. Look back at your notes. You should see that this is true as we go through everything. How to find where we are in the titration. I'm just going to say that that's your BCA table. So, and the pH at the equivalence point. So I'm going to assume that this stuff that I just did about products or reactants, that's going to do BCA table setup. This question here says, is there a really specific way when you're reading the problem to know whether you use an ICE or a BCA table or both? BCA is for strong species. So if you have a strong species, you are using a BCA table, period. I should also say, by the way, that this list of questions I just pulled from the whole class, so they didn't hear each other ask these questions. So if these seem redundant, that's because they just submitted them online and they had no idea what everybody else asked. Lebesgue successive approximation for the test. I answered this one already. See earlier answer. So I did that. Is the acetate ion the only common ion we didn't know for the common ion effect? No. We did, I think, deal a bit. On the original video for the exam review, we dealt with pH and KSP with solubility. It was actually an Alex problem. It was actually an Alex too. So there is that information, and we did talk about that in the original video. So I'm going to talk about BCA tables, where we are in the titration, the pH at the equivalence point, and solving volume. Okay. So your BCA table should have, so it's going to have a strong species. We're going to say it has a weak thing, and that makes a conjugate. We're going to go with this setup. You've got a BCA table. You do all the math in the moles. We're dealing with after. If you want to think about it for a strong titration, we could also think about this as the burette, the beaker, and that setup would also work for this. So essentially, if so we're going to have 3 different scenarios. If your strong species is gone, but you still have some of this, I don't know how much it is. I don't really care. But you have some weak. So that means you still have stuff left in the beaker. This is before the equivalence point. So if you finish your BCA table and you still have some of the stuff left in the beaker, you are before the equivalence point. You didn't react all of it away. It's still there. You are before the equivalence point. If we did this exact same setup, you know what? I'm just gonna make a copy of this. I didn't actually need all of it. Oh well, that's okay. And then I get to erase some things. So that's before the equivalence point. I got some of the stuff left in the beaker still. If I have no reactants left, I am at the equivalence point. I reacted everything away. The moles of the stuff from the burette are the same as the moles in the beaker. I reacted everything away. I will have conjugate stuff, but I reacted everything away. I am at the equivalence point. That after part of the BCA table tells me where I am. Last but not least, we have a strong thing. We have a weak thing. We have the thing in the beaker. The thing in the beaker is gone. The thing in the beaker is gone. But we actually have strong stuff left over. So you are now after your equivalence point. So that means that you just kept adding more strong stuff. You didn't need to, but you just kept adding more strong stuff into the beaker and you overshot your titration. You went after the equivalence point. That means you still have some conjugate stuff there, but so basically you're following where the 0 is. If I am after the equivalence point, then I have nothing in the beaker, but I do have something left from what was in the burette because I kept dropping things in there. If I'm at the equivalence point, then I actually have 2 zeros. If I'm at the equivalence point, both of my reactants are gone. If I'm before the equivalence point, I got rid of all my strong stuff, but I have weak stuff left over. And then this is the part that I then have to worry about because I still have weak stuff left over. And if my conjugate species is weak, I have to worry about that too. So looking at the after of your BCA table tells you where you are in the titration. Oh, pH at the equivalence point. I thought we already did that. Again, I'm getting redundant questions. I did already do that. Okay. So I did actually address what the pHs are at different equivalence points, looking at 7 for strong acid, strong base, looking at greater than 7 or basic for a strong base, weak acid, looking at less than 7 or having an acidic pH if you have a strong acid, weak base titration. So we did actually cover that in the original review, but it is an important question. So for those of you that are like, why did she do that twice? It is important. It is a thing that you should know. So that's why I didn't mind being like, oof, yeah, let's talk about that if I didn't talk about that already. But we did talk about that. We just did it in the exam review before. Okay, titration problems where you need to find the amount of volume needed to reach the equivalence point. Yeah. So, oh gosh darn. Sorry, that gosh darn is because I worked on my what's it called? That thing. Workshop for Friday. And honestly, I don't care what's new in Word. And I was just like, could I just have my workshop real quick, because I'm just going to nab the problem that I've already looked at. This guy. So, because the question is, how do we deal with asking essentially for the pH at the equivalence point when there's no volume given? And I think this was an Alex, but it's a good question. It's a valid question. And the goal is find pH. Oh, I should also have a Ka value for that. 6.2 times 10 to the negative 10. 6.2 times 10 to the negative 10. Okay. So two things before we get started. One, this question will be kind of long. Two, this is a great question for Saturday. So I do recommend that you know what this is. So my goal is to find pH. I do have the word titrated. That's helpful. I've got HCN. That's a weak acid. Also, there's a Ka value for HCN. It should be better worded. And I have this other thing here, which I can recognize as a strong base. I have a strong base. I'm going to go ahead and set up a BCA table, because that's what I do when I have these species. Plus HCN is going to make CN minus and water. Now, here's the weird thing here. B, C. Hey. So here's the weird thing in this problem. It just told me that I'm at the equivalence point. So I actually have extra information, which is at the after, I should have none of these things. So since I'm at the equivalence point, I actually already know something about my BCA table, that I should have none of that present. So let's see what else I know. Now my BCA table is always in moles. So I'm going to take that milliliters, that 0.034 times 0.23. And that gets me a number of moles of HCN, 782. Again, moles. We need moles. I don't have any of that weak base. And it didn't actually tell me about the sodium hydroxide. But because I know that these are 0, I know in order to get to that I should take this number of moles, and this should be minus my moles here, plus my moles here, and that I should be able to subtract the same number of moles here and get 0, which means this number of hydroxide has to be identical. So I should actually be able to fill all of that in, given just the moles of the weak acid and the fact that I'm at the equivalence point. So the fact that I'm at the equivalence point is the only way that I know all of these things. So I am relying on additional information. I'm relying on that point about the equivalence point. That is a major part of how this works. So from there, since I'm at the equivalence point, I know I have an amount of my weak base. Since my weak base is the thing that I have, and this is in moles, the goal of the question says to find pH. Well, I'm at the equivalence point, so if I'm going to find that, I need to take my weak base, mix that with water, and get the weak acid back and hydroxide. This is an ice table. Ice tables, I have to have molarity, which means I need moles divided by volume. So I have 0.00782 moles, but I need my total final volume. This is 0, that's 0. Water I don't care about. So I do need more information. So what I need is I need total volume. The problem only gave me one number. So I actually have to find my other number for this. So what I'm going to go ahead and do is I know that my 0.17 molar, I'm going to use the definition of molarity. I'm going to use that molarity is equal to moles divided by liters. So my sodium hydroxide molarity is 0.17, and that I already found the moles. It's that 0.00782. So 0.00782 moles. And then I'm just going to use the equation essentially to solve for liters. It's supposed to be a little x. So that way when I solve for my liters, I get 0.046. And then I'm going to add to that the liters that I had before, which is my 34. So I get 0.08 liters. So that's my new total volume. So my total volume goes over here. So that did need to be a total volume. I did have to go figure out the volume of my strong base. So even though I wasn't given a volume of the strong base, I could figure that out because I had information about the moles. I was actually talking to some students about this in office hours. They actually reminded me, I forgot, if you believe that, that the other way to do this one is you could have done M1V1 equals M2V2. So you also could have said that because the moles are equal, you actually could have taken the molarity in the milliliters here, and you could have said that I've got 34 milliliters of my acid and 0.23 molar, and my base is 0.17 molar, and I'm solving for volume, and you would have gotten the same number. So this is another strategy. This is a Gen Chem 1 strategy. So if it's not familiar and you're like, I don't know what they're doing, but there's my 46 milliliters, and 46 plus 34 is still 80 milliliters, which is still 0.08 liters. So anyways, so other students reminded me of that. So that's the main reason why I'm sharing that as an option, because maybe for you too, you're like, oh, they asked for volume. I can use M1V1 equals M2V2. If that's you, this absolutely works, by the way. That was not how I was going to do the problem, but students reminded me of it, and they are correct. This absolutely works. So now I have an ice table problem. Yay, an ice table problem. I know you're all thrilled that we have gotten this far and gotten to an ice table problem. So now I'm at minus x plus x plus x, 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 whatever that molarity is, which I now need to figure out, 0.00782 divided by 0.08 is 0.097875 minus x. I have hydroxide. That means this has Kb. So this is Kb is equal to x squared divided by 0.097875 minus x. I need Kb. Crap. What do I have? Ka. I don't want Ka. Sorry to sound like a small child. Down here, Ka. So I have Ka from the problem. 1 times 10 to the negative 14th is equal to Ka times Kb. So therefore I can solve for Kb. 1 e negative 14 divided by 6.2 times 10 to the negative 10. The way that I knew I had to do this, since I don't think I made it clear in my aggravated sounds, is because I have hydroxide. Hydroxide means I have to have Kb. So Kb is always hydroxide. Ka always has protons in the product. So that's part of the definitions of those things. So since I make hydroxide, this has to be the Kb. So my Kb is therefore 1.6, myself one more digit, times 10 to the negative 5. We could go ahead and take that moment. God, I hope this works. Otherwise, I'm in big trouble. To do 400 times the Kb and compare it to the initial concentration. Honestly, we're going to set you guys up so that this works because this problem is really long. There is no way we would make you guys do a quadratic because this problem is so long as it is. But that is in fact smaller than my point 0.097. So we can use x is small. It will work. Yay, thank goodness. So this subtracted x is therefore 0. So therefore I can just continue to solve. So I've got my Kb, and I'm going to multiply it times the initial concentration. So therefore I get something like x squared is equal to 1.58 times 10 to the negative 6. And then I'm just going to square root both sides, and I get x is equal to 1.26 times 10 to the negative 3. That's molar. Since we're using Kb, we used Kb because this makes hydroxide. The original question did actually want pH. So therefore, when I take the negative log of this thing, that is going to be pOH. So I am going to take the negative log of this because I personally think that that's a little bit faster than my other strategies. But that does in fact give me pOH when I do that. So pOH is equal to 2.9. pH is going to be 14 minus my pOH. So that's 11.1. That's the answer to the problem. Gosh, that was long. So that is a really long problem. Don't get me wrong. But I do recommend that you try this one out on your own to make sure that all of the steps make sense. Because this is a great problem to practice for the exam on Saturday. I actually think that's definitely all the questions I have time for. I think that actually does cover all the questions that I got both from class and the follow-up. Office hours are still happening, peer tutoring still happening. Good luck, guys. You can do this. I'll see you guys at the exam. Exam's on Saturday, 10 a.m. Bye.